Hello, everyone. Thank you for having me here. My name is Jamie Miles. I'm an NIHR Clinical Doctoral Research Fellow in Yorkshire, a paramedic in Yorkshire Ambulance Service, and an RChem trainee ACP in Barnsley. I'm here to present Beyond Regression, Choosing Machine Learning in Emergency Medicine. Let's begin. And just a disclaimer, none of this is new. Logistic regression, or at least the logistic function, was theorized by Verhulst in 1838. Alan Turing described the learning machine in 1950. What is increasingly novel is the wealth of data we now collect digitally in healthcare, which is acting as a bridge between statistics and computer science. Before we delve right in, I want to show you Drew Conway's Venn diagram of data science. This is important because actually these all exist in the same space. Statisticians would argue that machine learning methods such as neural networks are actually just generalized nonlinear models. And computer scientists would argue that logistic regression is just another supervised machine learning method. As a clinician, I just see it as one big toolshed that I can use to help make predictions in practice and hopefully improve care. I'm going to start with a quick and dirty refresher into regression, and we'll start linear. If we want to explore whether an independent variable, x, or predictor variable, is associated with a dependent variable, y, or response variable, we can grab some data, plot it on the graph, and come up with a line of best fit. This line will give us some answers which will allow us to make future predictions. It will tell us the intercept, alpha, which is where the line crosses the y-axis. This is also known as the constant, and it's the value of y when x is 0. It will tell us the slope, or beta, which is how much y goes up or down for each movement left or right on the x-axis. And so if we wanted to make a prediction, we would use the following equation. Well, y circumflex, and circumflex means estimated, equals alpha plus beta times x. Now, our data is a hyperbole, as it falls exactly on a 45-degree angle. But if we plumb in the numbers for someone who hasn't had a meal break for 6 hours, we can see that their level of hangriness is predicted to be level 80. But there are limitations to linear regression. It assumes linearity in the coefficients, the betas. The y will always have the same relationship with the beta. Also, it doesn't really handle categorical or binary outcomes very well. In logistic regression, we can take these types of outcomes and transform them to estimate their associated effect size. Taking the exponential of these gives us the odds ratio for each unit increase. This is more interpretable in clinical practice. Here's an example table taken from a 2017 study in the BMJ examining the risk of dying following discharge from the ED. It's a multivariable model, which means multiple features were examined against the dependent binary outcome of death. Note that all the odds ratios have confidence intervals with them. A quick cheat sheet is anything crossing over the 1 is statistically insignificant. Take rural location, for example. The odds ratio is 1.1, but the confidence interval ranges from 0.98 to 1.24. Therefore, we can't say for certain there is an association between living in a rural location and dying following discharge from ED. Using regression methods have many benefits. They are explanatory as well as predictive. You can use it to explain associations and also to predict outcomes in new patients. They are also fast to create and easy to interpret, and they rarely overfit the data. Overfitting is where you create a model that's too perfect, and when you test it in another area, the performance crashes. There are occasions they can overfit though, such as when the data is high dimensional or you have less observations than the number of features you want to include. Regression methods have worked well in healthcare data where only limited variable information was available. But data collection has changed, and we now produce a plenitude of digital data every day about our patients through routine collection. Regression has its flaws, and this is where machine learning might help with the answers. With logistic regression, you have to specify the model to fit. This might involve cherry-picking variables to go into the model. With machine learning methods, though, you don't have to do this. You can have no prior knowledge and put all the variables in. And, if you have lots of features, the regression model can struggle if they are collineated with each other. This is known as multi-collinearity. You can upgrade the regression model to include fun features such as regularization penalty, like ridge, elastic net, or lasso. These will strip out the variables that lack an association, but it doesn't solve all problems. With machine learning, you can take the collineated variables and transform them into a single new variable. And the instances where a regression model may overfit that I mentioned before, a machine learning method such as principal component analysis can handle that. Playing with data in the age of digital healthcare is like an iceberg. When the research is published, you may only see the model, but underneath the water is a tremendous amount of work that's required to get the data to being model ready. Machine learning methods are really useful in helping with this data wrangling. They are a tool to help explore the utilization of data, and they don't have the same assumptions of standard statistical methods. They can also handle more data types such as images and free text. Machine learning algorithms all have different mechanisms, and depending on what data you have or what problem you want to explore, they might offer a better solution. I'm going to introduce some of the mainstream machine learning methods and illustrate how they've already been used in emergency medicine. I'll start with tree-based models. Trees are quite a useful method as you can grow trees that perform regression or trees that can classify an outcome. The decision tree uses a clever method known as recursive partitioning to find the best split in every variable. Take this example from Steyerberg, who used a decision tree to predict mortality following AAA surgery. The very top node is known as the root node, and from it we have two branches. The one on the left goes straight to a leaf, or terminal node, which is a classification. On the other branch, it leads to another decision node to find out more information. As we can see at the bottom, there are 4 leaves, and these are all classifications of risk. We have congestive heart failure at the top, and this is no accident. In tree-based modelling, the splits are evaluated on how much information is gained from the node. This allows us to prune the tree, where we can put the most informative node at the top and remove sub-branches. In this example, the tree has classified congestive heart failure as the highest risk of mortality. One decision tree might not be accurate though, so we could come up with a whole forest of trees. Much better. Sometimes though, the nodes can be very noisy. Take age for example. This can be a really loud variable, especially in the context of disease. In order to stop these from dominating the forest, we can tweak our forest, introducing some randomness. One of the major benefits of using random forests is that it can be used to impute missing values within a dataset. Sometimes, especially with electronic health records, the data can be quite complex. Now, Levin et al. Used random forests to classify patients according to the Emergency Severity Index, the ESI. They built an e-triage algorithm and compared it to the routinely collected ESI recorded in the notes. They found that the e-triage more accurately classified the level 3 patients, the mid-acuity. Machine learning algorithms can also retrain by using labeled outcomes to rebalance the weights and biases used in the model. A really good example of this is in a neural network. This is a close neighbour of logistic regression, as each node is in effect its own regression algorithm. As the data is classified, it moves to the next layer of nodes for further classification. This keeps happening until it manages to classify the outcome. Here is the same AAA example from before, but in a neural network. If it misclassifies an outcome, it will learn by backpropagation, where it will tweak the coefficients in each node and try again, in effect, retraining. It has shown success in many areas of emergency medicine. One such is Smith et al., who used a deep neural network to classify ECG abnormalities. They compared it to the best contemporary algorithm by Veritas. They found it correctly identified a major abnormality in 92% of cases compared with 87%, and they correctly interpreted the ECG in 72% of cases compared with 60%. Other methods can be used to turn language and free text into data we can work with. Take Sufi et al. In 2018. They used a method known as fuzzy logic classifier to turn the areas of subjectivity of the ESI user into data which can be used to classify patients into the 5-level emergency severity index. Even further than this, Sterling et al. In 2019 used a method of machine learning known as natural language processing, or NLP, to analyze nurse triage free text forms. Their model had an area under the curve of 0.79 with a narrow confidence interval. Increasingly, we are seeing studies which are applying numerous methods to their data to find the right model choice. A good example of this is Goto et al., who looked at the machine learning of clinical outcomes for children during ED triage. They used logistic regression with a lasso penalty, a random forest, a gradient-boosted decision tree, and a neural network. They then produced a comparator ROC curve and decision curve. This is useful for the readers to see how each model performed visually. They were all quite similar, but decision trees and neural networks outperformed the logistic regression. With software such as R, Python, and Orange, it is becoming increasingly possible to simply run multiple algorithms on the data and test for the best performance. But never underestimate the time and expertise you may need to get the data to a point you can run an algorithm. Even with machine learning, you need a statistician to help with this navigation. So, to sum up, logistic regression has many benefits and is the industry standard in emergency medicine. But there are other tools in the shed that may offer a better solution depending on what data you have. The bottom line is, don't pick the data that will fit your model of choice. Pick a model that can appropriately handle your data and give the best result.